In this video, I'd like to introduce you to the Boltzmann distribution curve. We're going to use this curve to explain why using a catalyst and how changing the temperature of a reaction will affect the rate of reaction. Okay, here's the basic Boltzmann distribution curve. The area under the curve represents the total number of molecules. We can see that there is a distribution of energies for these molecules. Think about all the gas molecules for the room that you're currently in. Some of those molecules will have very, very low energies. Some of them will have very, very high energies. But most molecules have round the average energy. It's a bit like shoe size. Some people have very, very small feet. Some people have very, very big feet. But most people have average size feet. Okay. When we think about activation energy for a chemical reaction, activation energy is the minimum amount of energy that particles need to have for them to be able to react successfully. So let's just draw on an activation energy. All of the particles represented by this shaded area, which have energy greater than the activation energy, will be able to react. Think about an energy profile diagram. This should be really familiar to you by now. When we introduce a catalyst provides us an alternative pathway which has a lower activation energy. So more particles have enough energy to be able to get over that lower activation energy, so the reaction gets faster. Well, when we think about adding a catalyst provides an alternative pathway with a lower activation energy. So we can now see that there is an increase in the total number of particles with energy greater than the activation energy. We have the original number of particles plus these extra particles which have energy greater than the new lower activation energy. So a greater percentage of particles are able to react and the reaction gets faster. This is the kind of thing that you could be asked to sketch in an A-level exam. The examiner is looking for the general shape of the curve. Make sure it doesn't cross the x-axis at high energy. Make sure it starts at the origin. Make sure you label the axes correctly. Number of molecules or number of particles on the y-axis and energy on the x-axis. We can also use this shaped graph, the Maxwell-Boltzmann distribution curve, to explain how temperature is able to change the rate of reaction. Here again we've got the basic shape curve. If I increase the temperature, I'm going to increase the average energies of the molecules. There will be still some molecules with very small energies, but that will be a smaller number. There will be more particles with higher energies. The total number of particles will still be the same. So the peak or maximum of the curve moves to a higher energy, but it also moves lower because the total number of particles has to be the same for the two curves. If I now think about my original activation energy, this was the number of particles with energy greater than the activation energy which was able to react. At a higher temperature, the activation energy remains unchanged, but we can see there has been a massive increase in the number of particles with energy greater than the activation energy. So a greater proportion of particles have energy greater than the activation energy, which is why increasing temperature will increase the rate of a chemical reaction.